Good morning. My name is Ryan Moe, and this is my senior project, the Balsa Wood Bridge. There were several requirements for this project. I had to design a balsa wood bridge out of only balsa wood and glue. It could only weigh 85 grams, and it had to hold 20 kilograms. So it could only weigh about the weight of half a smartphone, but it had to hold about 45 pounds. Along with that, it had to be 400 millimeters long, and it had to have a solid road deck that was of a certain width so that like a pretend car could drive across the bridge. Along with that, it had to articulate, so it had to raise up to 140 millimeters from the midpoint starting from the initial position. That also had to happen. It had to raise up in 10 seconds, and I had to complete a full cycle in less than a minute. So here are some of the results I had. This graph shows the articulation of the bridge. So this bottom line shows the amount of time it took to raise, and the top line represents the full cycle. As you can see here, it only took about 3 seconds and 6 seconds to do both of those measures, and the maximum time was 10 seconds and 60 seconds. So it did a really good job. It was very efficient. And down here is the table showing the amount of weight that the bridge ended up holding. You can see it broke at 31 kilograms, which was much higher than the 20 kilograms that it was required to hold. So those are some of the results, but let's go back to the start of this project. So here's some of the analysis that kicked off this project. The first thing I wanted to do when I was working on this was figure out how much balsa wood I had to work with. So this analysis down here shows the amount of balsa wood that I had to work with, and it was not a lot. So the next thing I did is I knew I had to build a truss structure so that I could support the amount of weight and span the large gap that was required. So I did some research into balsa wood, and I found out that it was 30% stronger in compression than in tension. So I chose a truss that I designed that was stronger in compression and had more members in compression than in tension, so that I could use the full extent of all the materials at my availability. After that, I found out how much weight each of these members had to hold, and then I found the minimum cross-sectional area for each of those members. So some members, like these top ones, are thicker than these diagonal ones, and that's because they had to carry more weight. So these top ones had to have a cross-sectional area of about 200 millimeters squared, and the diagonal ones only had to have a cross-sectional area of about 106 millimeters squared. I also had to find the weight of the glue to ensure that the glue wouldn't push the weight of my bridge over the maximum amount of weight. And I also calculated the total strain on the string when I was articulating the bridge so that I was sure that the string wouldn't break while I was doing that articulation test. So once the project was all thought out, it was time to start construction. So once I found out the pieces that I needed, I ordered balsa wood sticks online, just like this. These came at a predetermined depth and width, so I could just cut them down to size without having to worry about either of those measurements. Ordering sticks was the most cost-effective way to get my materials instead of ordering them special made or in a big block of balsa wood. You can see in this first picture here, I cut down strips with a miter saw, and here is another picture of the strips once they've been cut down. And some of them needed to be cut at angles, so I used the miter saw for that as well and ended up with angles like these. And then this is the road deck that I also ordered a strip of and cut it down to size, and then drill a hole in the middle so that it could be used for the strength testing. I also had to glue the pieces together, and I wanted to use a very strong glue because I knew that I didn't want the glue to break before the wood, because if the glue broke before the wood, then that meant that all of the truss that I chose that was 30% stronger and all of the cross-sectional areas wouldn't be important because the glue would have failed first. So I chose to use a polyurethane glue. It also didn't have a super high density. There were a couple manufacturing issues. For one, this little beam here, I ended up accidentally cutting. I switched the depth and the width, so it's supposed to be cut at 1/2 inch by 3/8 of an inch, and I ended up cutting it at 3/8 of an inch by 1/2 inch. So I went to glue the truss together, and this piece did not fit, so I had to go back and recut a couple pieces. There was one more issue in that when I first started gluing the pieces together, I noticed that the weight was over the limit, so I had to go back and sand down the trusses. And then luckily when I looked at the sizes, it was still at the minimum cross-sectional area for each of the pieces. Then the project was all put together, so I glued together the trusses first, and then I connected the trusses to the road deck, and then I built the articulation structure. So I had this tower, I glued this shaft on, and I put the reel on, and then I connected the string through the reel over the shaft and onto the bridge so that it could lift. This tower is actually made out of a bookend. It was one really efficient part of this project. It was easy to order and it fit my needs perfectly. Now for the testing portion of the project. So there were 4 main tests or confirmations really that I had to do for this project. The first one was the weight test. So I just measured that with a scale. I had to make sure that all the dimensions of the bridge were correct, which I knew would be correct because of the construction process. I had to do the strength test, where weight was hung from the bottom of the bridge, and I did the articulation testing, which measured how high and how fast the bridge would articulate with the lifting mechanism. So the weight test was really important for this project because it was one of the main parameters used to determine the functionality of the bridge. So that was a really important test for me, and it had to be under 85 grams. And as you can see here, the final weight of the bridge was 80 grams, which is exactly where I wanted it. It gave me a little wiggle room and still used as much of the resources as I could. I also had to recheck the dimensions to make sure that everything was within range, because if I didn't do the weight test and the dimension test, then the strength test and the articulation test would be invalid because the bridge wouldn't be correct. So next I did the strength testing, which can be seen here. So there's 2 tables 400 millimeters apart, and the bridge is in between those. I used this piece, which I attached to the bottom of the bridge and hung a bucket on and added weight incrementally. This right here is exactly at 20 kilograms, which is the amount of weight that the bridge is required to hold. There was one slight issue with this connector piece that can be seen up here. The bucket was situated to the side of the connector piece and caused it to tilt, which gave an uneven distribution of weight on the bridge. But I added this rubber band, which kept the bucket in place, and there were no more issues with the strength testing. It ended up holding 31 kilograms, as I said, which is 150% of the total amount of weight that I was hoping it would hold, so that was a really good outcome for that test. Finally, there's the articulation test that can be seen here. So the setup for this test was to use a measurement stick to ensure that it hit the weight or the height limit. So in the middle you can see this stick right here. This is exactly at 140, and in this test it actually goes all the way up to 160 millimeters. But I had to ensure that it reached that threshold. I took a recording of this and then went back and saw how much time had passed, and that's how I got the results for my graph. It was very fast and very efficient as far as the lifting mechanism goes. So that was all of the testing. And now on to the schedule and the budget. So here's the schedule. As you can see, most things progressed on time and the project moved forward in a linear fashion. There were some things that got behind and caught up on, but all those things were able to be worked out before it became an issue. Here's the budget summary. I ended up spending 6% more money than I had allocated for the project originally, but that was due to high shipping costs for all of this balsa wood, and I wanted to ensure that there was enough balsa wood that if there was a mistake made, it wouldn't incur extra costs, such as this piece here, which was a mistake, and I needed the extra balsa wood. So that's my senior project. It was a lot of fun to work on, and it really furthered my understanding as far as all of the engineering processes go. I'm really proud of my results as far as the 2 main tests that I did, the strength test and the articulation test, and I think it made me a better engineer. Thank you.